Hello everyone, welcome to this word example. When a child is sitting on a swing, the motion can be considered to be a swinging pendulum. In this motion we do not consider the vertical position or the horizontal position, but we only look at the angle between the mass and the equilibrium position. So in the lecture it was told that this motion would follow the following differential equation. This differential equation was L times the second derivative of theta is equal to minus g times theta. When you work this out, you will see that this theta is a sinusoidal function with the angular frequency is equal to the square root of g over L. Well, before we go further with the rest of this work example, I just want to point out something. This differential equation only holds for small values of theta. When theta becomes too large, this is not valid anymore for reasons that are very complicated, so do not worry about that, but just keep it in mind when you're doing the exercises. When we want to determine the period, we have to plot our function against time. And we can see that the period is the time it takes for the swing to go back and forward, indicated by this line. Well, we also know that period is equal to 1 over the frequency. And when we go back to our equation for our theta, we see that the angular frequency is equal to the square root of g over L. But we know that the angular frequency is equal to 2 pi times f, and therefore f is equal to the square root of g over L divided by 2 pi. We also know that t is equal to 1 over f, so therefore t is equal to 2 pi divided by the square root of g over L, and therefore it's also equal to 2 pi times the square root of L over g. So now we will focus on the angular velocity. For linear motion, it holds that the linear velocity is equal to the derivative of the linear position, so v is the derivative of x. For angular motion, the angular velocity is equal to the derivative of the angular position, so omega is the derivative of theta. We already have an expression for theta, so we can take the derivative of that by using the chain rule, and we get that the omega is equal to the square root of g over L times theta 0 times the cosine of the square root of g over L times t plus v. And if we want to check what are the units of our omega, we can fill in all the units we have for our given parameters. So the units of g are m divided by s squared, L is in meters, and theta is in radians. Note that the cosine is always a number between -1 and 1, so this does not have a value. We can work out the fraction and we see that we get a square root within 1 over s squared times radian. And if we work out the square root, we can see we have radian per second. And this makes sense because the angular velocity tells us how much radians we pass by in 1 second. So here we have your equation for the angular velocity. When we plot this together with our angular position, which is theta, and plot it against time, you can see they are out of phase. And this makes sense mathematically because they are a sine and a cosine. But it also makes sense when you think about physics, because when you're on a swing, the point where you go the fastest is when theta is 0, because then you're close to the ground. In the other way, you can also say that the maximum height you get is when the velocity equals 0, which you can also see in the graph. So if you want to determine how high can we get with our spring, first we have to look what is our maximum kinetic energy we can have. So the kinetic energy is given by the formula 1/2 times mass times v squared. So the maximum kinetic energy is 1/2 times mass times the maximum velocity squared. But note that this is a linear velocity and we have angular velocity. It was given that the linear velocity is equal to the angular velocity times the length of the pendulum. We already have an expression for our angular velocity, which is the square root of g over L times theta 0 times the cosine of the square root of g over L times t plus v. We multiply this with L and we get our following equation, which is the linear velocity is equal to the square root of g times L times theta 0 times the cosine of the square root of g over L times t plus v. If you want to determine what is our maximum value for the velocity, we can look what is the maximum value our cosine can get. Well, the cosine is a value between -1 and 1, so the maximum value is 1. So the maximum value our velocity can get is the square root of g times L times theta 0. If we fill this in for the equation for the maximum kinetic energy, we can see that our maximum kinetic energy is a half times mass times g times L times v 0 squared. So if you want to know how high can we get, we assume that all our kinetic energy is transferred into potential energy. So our maximum kinetic energy is equal to our maximum potential energy. We just derived the equation for the maximum kinetic energy, and we know the equation for the maximum potential energy, which is mass times g times the maximum height we can get. We can set those two equations equal to each other, and we see they have some terms in common. First, we can cross out the m's because they're on both sides. We also see that g is also on both sides. So we cross that out. This leaves us with the equation that the maximum height we can get is a half times L times v 0 squared. So to recap what we have done today, we looked at the motion of a swinging pendulum, where the motion can be described in the differential equation, which is L times the second derivative of theta is equal to minus g times theta. This gave us a solution which is a sinusoidal function with an angular frequency equal to the square root of g over L. And with this we could determine the angular velocity, which was the square root of g over L times theta 0 times the cosine of the square root of g over L plus phi. This gave us the opportunity to calculate our maximum height, which was equal to a half times L times theta 0 squared. So thank you all for watching, good luck with your exercises, and see you next time.